Hello everyone, my name is Geoga. I'm a PhD student at the Department of Statistics at Rutgers University, and I'm going to talk to you today about BesselK.jl, which is a differentiable implementation of the modified second kind Bessel function knew. So, TLDW here, if you don't really care about implementation stuff, just swap BesselK for AD_BesselK and put the package BesselK.jl into your dependency tree, and voila, now you can do derivatives with respect to the order parameter new. So for those of you who are interested, again, talking about one function, I recognize it's a narrow scope, but I think that there's some stuff in here that will be more generally interesting. Knew is defined as one of the solutions to this differential equation that I'm showing you here, and software to evaluate it is not really new, right? The Amos library that SpecialFunctions.jl uses is like from the 80s, and it's great, and it's very tested, and it works well. And derivatives of knew with respect to the argument x, they exist, and you actually write them in terms of knew again, and so you can use the existing libraries for that. But derivatives with respect to the order parameter are not so simple. Technically, they do exist in closed form, like I'm showing you in the screenshots from this paper here, but I think good luck implementing that, or at the very least, if implementing it sufficiently accurately without making it so slow that it's not very useful. But I really want the derivatives, right? I want to fit the Matern covariance function with derivatives, including the order, which we would call the smoothness parameter. So what are my options? I'm not going to implement those things, those exact expressions above that I'm showing you. Finite differences work pretty well in most parts of the domain, but not near the origin where there's a singularity, which is not surprising, right? At least non-adaptive ones don't, and adaptive ones are, again, pretty slow. So the thing that we decided to try to do was to re-implement the function with the explicit goal of passing AD through it, right? Instead of implementing the derivative, we implement the function specifically to pass AD through it. And it's not trivial to do that. And, the first hurdle is, of course, that, for any special function implementation in general, right, you have to cut up the domain, and different numerical strategies work well in different places. So you got to do that. So, here's a diagram from the Amos paper, for example. But there's kind of a new problem that we want to deal with that older libraries didn't really have to deal with, which is that the code needs to encode the derivative information. And that's kind of this is kind of the general problem that I'm hoping will be appealing to people beyond, the fans of knew. Here's an example of what I mean. Check out this function bad sign of x, which, just checks if x is 0 and then manually returns sign of 0. You can see how when you do that, you cut the dependency graph for this function with respect to x, like at the origin. And if you imagine what forward diff is doing, right, make a dual of x and put it into this thing, and if x is 0, then you're asking for the derivative of the function f of x equals 0 with respect to x, and that will be 0. So that's not going to work. And, of course, no one's going to implement bad sign, as I've written it here, but I think a lot of people will have a function where in certain specific places you can manually take a limit, or you have to manually take a limit, or you can simplify in some way or something like that, and this problem of argument-dependent control flow can really get you into trouble. So, what does it have to do with special functions? Well, it kind of comes up a lot, actually. So here's a really convenient recurrence that exists for knew that I'm showing you at the top of the screen here. So, a way that you might use that is for integer orders, you would come up with some fancy approximation for new equals 0, new equals 1, right? K0, K1. You do the remez, on this or that part of the domain, whatever, right? So say you have that, and then you can just kind of do this forward recursion. You can get kn for any n. But now you want the derivative of knew at new equals n for some integer n or something like that. Can you use this code? No. Simplest explanation is, one of the potentially several problems with doing this, right, is that at the bottom of the call stack, these functions, BesselK, new 0, new 1, they're not even functions in new. So of course, again, just like bad sign, that's going to give you zeros, and those are going to propagate up until you're going to get 0 back. So how do we fix this in BesselK.jl? Which, by the way, BesselK.jl doesn't give you 0 in that case. So how do we handle it? Well, it's just this very painful problem of making sure that every branch in the argument-dependent control flow preserves that derivative information, and it's potentially painful to do. So again, a quick analog solution again. Check out this better sign function, where now instead of checking that x is 0, you check that x is in a neighborhood of 0, and If it is, then you substitute, polynomial expansion of sign at 0. That's very accurate for a sign sufficiently near 0. And now you can see how both sides of the branch in that control flow, they will give you at least very, very accurate derivative information. In the case of the polynomial, it's maybe not exact, but pretty accurate, right? And there's no cutting of the dependency graph, and everything, each branch will give you, anyway. So hopefully hopefully this is clear why that solves the problem. So this comes up a lot, and it's a closing example here. I'm just going to give you a couple harmless looking little functions that show up in some intermediate quantity in our implementation here. So check out in particular this function gamma1 here. I think when you look at that, you can see, you might guess that this function is of course very well behaved at 0, for example, which it is. But there's a problem, which is that if you literally write the code definition, if you write gamma1 of nu equals and you literally translate this exact expression to the code, then that's not gonna work for you at certain values like 0, because you're going to be dividing by 0. And so I think the first thing that someone would think to do to fix that is to manually insert the limit, right? If nu equals 0, then return blah. And I think this, it's just a nice example because that doesn't work. At least if you want derivatives of gamma 1, that doesn't work. And so you have to go a step further than correcting with just a simple control branch. So moving on, now a few comments about the speed. I didn't expect to be able to beat the speed of the Amos library, but we did. And in some places by a shocking amount. And I think that was pretty interesting. And I think it says a lot about Julia that someone who's not a numerical analyst, which I am not, right, that I can just kind of write code and try to be thoughtful about performance and really get the performance for it. And that's pretty cool. Another interesting benefit here of rewriting this in Julia is that, again, I can also use AD for the argument derivatives, and they're a lot faster than the exact derivatives, right? Which, as I'm showing you here, you can really nicely write them in terms of 2 calls to k nu. But if SpecialFunctions.jl is much slower than our BesselK, then 2 SpecialFunctions.jl calls is definitely going to be slower than 4 diff.derivative of our BesselK. And that is true. And as you can see in this table here, which I don't really have the time to discuss in too much detail, so our implementation here is knew, and the ka is the Amos library. On some special branches, our code really does a lot better. And another nice thing about doing this in Julia is that you don't really have to choose between something that is like going to work for every type of new input, like a dual number or something like that, and the fastest performance branches, because I can use dispatch to deal with that problem, right? So, for example, when nu is k plus 1/2, or k is some integer, the function reduces to an exponential times a polynomial, and that's very fast to evaluate. And so I think an astute listener would say, oh, well, you just explained to us why you can't do that. And you're right, I can't get the derivative from that, but I can get the function evaluation from that. And it's much faster, and I can use dispatch. I can check if nu is, for example, an abstract float, and I can give you the fastest one possible. And so you can see here that the Amos library doesn't do that, or I have to imagine it doesn't, because 10 nanoseconds versus 50 is a significant gain. So that's pretty cool, and I think again it speaks to the power of Julia. So here's the anticlimax if you want to use this package. Just swap in BesselK for AD BesselK. Done. And that method and the similar one, AD BesselK XV for this modified form, those will use SpecialFunctions.BesselK wherever possible. And wherever it's not possible, then you'll get the Julia native code, which is pretty darn accurate. Your derivatives might only be accurate to 1e-12 atolls. And that if that's not enough for you, then it's not enough, and I'm sorry, but it's hard to imagine anything besides like an adaptive finite difference being better than that. So considering the what you get in terms of speed for giving up those digits, I think it's a compelling sell. If you do use the package, please throw us a citation. It's one function, but it really took a lot of work, and there was a lot of kind of interesting problem solving that went into kind of cleaning it up. I expect we'll have a journal reference for it pretty soon. So again, please, if you're watching this in the future, we'd appreciate it if you'd look and check to see if there's an official citation. Quick summary here, in the case of time, right? Compelling speed trade-off. Shout out finally to Bessels.jl, which is a a kind of new project that is trying to re-implement all of the functions. It's very ambitious, and it's the code that's there and ready to go is very impressive, and I expect that some improved version of BesselK.jl will end up in there at some point in time, so that will be a nice home in the future. And thanks so much for your attention, and here are my references, and I hope to see you guys around.